So, a very good morning to all of you. I hope you can hear me and see my screen. Last week I took a break because of some work. Now we are back to our favorite job, that is lectures. I hope you all are well, fine. Now, before we took break, we were doing a few things on current electricity. We had looked at these formula very quickly, going through them. I is equal to dq by dt, j is ia, j is nqvd, where vd is drift velocity, n is concentration of charges, the resistivity is e by j, j is your current density, it's a vector quantity. The resistivity varies with temperature. R is rho L by A. I is equal to V by R. Ohm's law, our famous. Uh, then internal resistance concepts, and we have done power equations. So we have done all the basics. Today I'm going to take one more problem on current electricity. We already did one which talks about the current and resistances and etc. Another one I'm going to take is on resistivity, which I found interesting. So let's have a look at it. I'm just zooming in a bit, and you all can see this and read this problem carefully. Let me go through it once before we start solving it. It's a kind of a standard problem. Few of you will find it fairly easy. Few of you may find it fairly challenging. I really don't know exactly where it fits. Nevertheless, it's a long, comprehensive problem. So let's solve it. Resistivity of a semiconductor can be modified by adding different amount of impurities. So you know semiconductors are beautiful devices in electrical world. Their resistances can be changed with position, volume, etc. layer by layer by adding different concentrations of impurities. A rod of semiconducting material of length L and cross-sectional area A lies along the x-axis between x is equal to 0 and x is equal to L. The material obeys Ohm's law and its resistivity varies along the rod according to the rho of x is equal to rho 0 e power minus x by L. The end of the rod at x is equal to 0 is at a potential V0 greater than end at x is equal to L. Find the total resistance of the rod and the current in the rod. Find the electric field magnitude Ex in the rod as a function of x. Find the electrical potential Vx in the rod as a function of x. Graph the functions rho of x, E of x and V of x for values of x between x is equal to 0 to x is equal to L. So you can see that's a straightforward integration function or integration problem. All I need to do is first put my coordinate axis, diagram, etc. into perspective. So let me draw my diagram. You need a rod of length L. So I will just draw it, say using a brush effect. This is the rod of length L. I would place the origin x is equal to 0 at one end. So let me do that. I would say that this is y-axis and this is my x-axis. Okay, and this point is x is equal to 0 and this point is x is equal to L. So all my calculations are between 0 and L. Okay, now what it says is the rho of x is following this, that is rho is I will just write rho is equal to rho 0. So you put rho 0 e power minus x upon L. So this becomes my basic rho is equal to rho 0 e power minus x by L. You can see that when x is equal to 0, this will become e power 0. E power 0 is 1. So at this end, resistance is, or resistivity is rho 0. Okay. While at this end, when you put x is equal to L, then it becomes e power minus 1. So resistivity here is rho at this end. At this end, resistivity is rho by E. So resistivity drops as we go from left to right. Okay. The end of the rod at x is equal to 0 is at potential V0 greater than. So we have put a potential difference also. That means it has been connected to a battery. Here the potential is V0, and here I can safely assume the potential to be 0. Okay. Now find the total resistance of the rod and the current in the rod. So finding total resistance is straightforward. So all you need to do is, in this case, you have to uh, since the if the has the resistivity been a constant, you could have written R is equal to rho L by A. But since it is varying, you need to use some of the integration techniques. So all you can do is you can divide the entire rod into large number of small segments. Each segments being infinitesimally thin. Remember, that's a very important idea. And having a width dx. And each segment has you can select one element at a distance x from the origin. Okay. Now, what will be the resistance of this element only this element? So if you want to find out the resistance of this element dx, then let us say that the resistance of that element is dr. Okay. So this resistance is nothing but, what do you do here? So you remember it's rho into length. Length of this small element is dx divided by cross sectional area, which I can take it as A. Let me see what is given. A, yes. So I can put this values. So I mean, you can put this value here. Rho value is given as rho 0 Ex by L. That will give you the resistance of this small element. Once you have put that, you have to find the resistance of the entire rod. That means you are dividing the rod into small intervals, very infinitesimally small, and then you integrate it over entire, find the resistance of one interval and integrate it over all the length. So total resistance R can be obtained. Instead of rho, I will write rho 0. I will write first the integration starting from 0 ending at L, and here I will write rho 0 divided by A, then what do I get here? I think e power minus x by L and dx. So this is what I will get to get the resistance, right? Now, how do we integrate it? So that's a straightforward. Almost all of you is a champion in these integrals. I will not waste time. Rho 0 by A is a constant. that goes out. Then e power x by L, integration of e power x is always first e power x, so that will come here, and then you divide it by minus 1 by L. That means you multiply by minus L, so L multiplied with a minus sign into you, I mean, yes, and then you have to put the limits of integration. This is integrated between 0 to L. So my resistance R will now be, if I keep this as it is, rho 0 L divided by A. Now if I put the values, so let me put the, let me first integrate from 0 to x for a general length. When I say 0 to x, that means I am finding resistance only of this section. That is from the origin to this point, any arbitrary point. Then later on, I can put x is equal to L and get the answer for the end also. So if I put higher limit as x, it will remain as e power minus x by L. If I put lower limit as 0, then e power minus 0. E power 0 is 1. Okay. So e power 0 is 1, and so it will be e power minus x by L minus 1. But I can absorb this minus sign inside. So I will get 1 minus e power x divided by L. Now the question asks that what happens if you put, what is the total resistance of the rod? So total resistance of the rod is now straightforward. It will be R0 L divided by A, and then here you get 1 minus e power minus 1. So this is the total resistance. Okay, so that part, first part is sorted out. Now what is asked is find the electric field magnitude in the EX. So you have to find out electric field. Electric field we have seen in our one of the lectures. Rho is E by J, so you will get you E is equal to rho into J. So I can use that fact that E as a function of X I'm writing, which I'm not writing actually, but that's what I mean. E as a function of X is nothing but your rho into J. Rho is now also a function of X and J. So if I put that, what is J? So J is the current upon area. So now I can put the value slowly. Rho I know, rho is rho 0 e power minus x by L. So rho 0 e power minus x by L. So this is my rho 0. J value is straightforward. J is, you know, it's current density. So it's a current I divided by area. But what is current? So current is nothing but V by R. V is V0, remember, difference, potential difference is V0, and R is this one. Okay, so I can write this little bigger equation now, that rho 0 by A stays here, and what comes in is I is nothing but V0 upon R. So V0 is here. If you have to write upon R, that means R0 L by A will come here. Not R0, sorry, rho 0. So rho 0 L upon A, which will go up. This all will come here. Numerator is e power minus x by L, and denominator is, what is denominator? This one, 1 minus e power minus 1, which is a constant. You can see that many things will cancel. Rho 0 and rho 0 will cancel. A and A will cancel. So all you are left with is equal to A upon, sorry, V0 by L. So I'll write V0, or I'll just leave everything as a constant. V0 by L 1 minus e power minus 1. This is all constant. So this is all K e power minus x by L. So this will help you to plot a graph uh, for third D part. Graph the functions rho x. So rho x, you can see this is rho x graph. If x is equal, we have already seen if x is equal to 0, then rho is rho 0. If x is equal to L, rho 0 is rho 0 by E. So that means it will drop exponentially. Similarly, you can plot the graph of R and E. So find the electric field Ex, find the electric potential in the rod as a function of x. So potential is V is equal to IR once again. So find the electric potential Vx in the rod as a function of x. So remember, if you take potential, applied potential is V0 at any point. Potential across the rod is I times Rx if you take any element, any distance, for example. So the potential difference between this and say at this point is going to be I into Rx. So potential will vary according to the equation V0 minus I times Rx. So you put the value of I as we have put here in this equation, and Rx from this equation, and if you solve it, what you will get is V0 and another constant. I may write it as K prime, and then leave you people to find out this K prime. E power minus x by L minus 1, or minus e power minus 1. So if you solve it, you will get this. Graphs are very straightforward. If you have to plot the graph, then graph of R against X, as we have seen, R against X, remember, if X is 0, look at it, if X is 0, this term is 1, and 1 minus 1 will give you 0. No, wait a minute. Let me see my notes. Graph the functions rho of x. So first function is rho of x. So rho of x we have already uh, rho of x, if x is 0, then e power 0. So e power 0 is 1, so rho 0, and x is equal to 1, so rho by e. So if you have to plot the first function, rho versus x, so it will start with rho 0 and it will drop like this to a value which is e0, sorry, rho 0 by e. This is how the first graph will look like. The second graph is asked is e of x. So e of x has a similar behavior, minus x by L. So this is what you will get. Third graph is v of x, just that your converging limits will be different, do remember. V of x, in v of x it's interesting. It is minus x by L minus e power minus 1. So if x is equal to L, then it becomes e power minus 1. So e power minus 1 minus e power minus 1 becomes 0. So basically what you get is, if you have a x and v graph, then it will terminate to 0 because the potential at the other end is 0. Okay, so that was good. Now it is time to take up, in next 5-10 minutes, it's time to take up the new topic. Remember, we are doing electricity and magnetism, so I will take up some of the revision of concepts in electricity and magnetism. Many of you must be familiar. I will quickly go through them, and next class we will take up some of the problems on them. So magnetism, as we all know, is now modern day view of magnetism is a relativistic manifestation of electric current. When the charges are moving at a high speed, they form electric current. Then in that case, if there is any other charge in the vicinity, then that experiences a force, and the magnetic field B can be defined using that force. Generally, the equation that we write to define magnetic field B is F is equal to QVB sine theta, or vectorially F is equal to QV cross B. So if you want to find or extract B from it, then B is equal to F upon QV sine theta. So that is the equation that we use to define. We can take this definition as definition of magnetic field, because force has already been defined in much earlier in physics. How does this equation work? So very straightforward. If you have a magnetic field B in one direction, and if you have a moving charge in some other direction, say V in this case, in this direction, then you have to curl the right hand fingers from V direction to B. Remember, this is very important. So if you can exercise your right hand palm, curl it around these vectors, perhaps will give you the direction of force. So outstretched thumb gives the direction of force, remember. Now what is important here is we can have two components, a component perpendicular and a component parallel. So component perpendicular is nothing but the sine component that comes here. So when you write it as QV sine phi into B, so V sine phi is nothing but the perpendicular component. So what it means is the velocity can be any direction, but its component perpendicular to magnetic field is the important component. It's that component which is responsible for the force. The component parallel to the magnetic field is not responsible for the force. So do remember that. Because in certain problems you need to differentiate between the two components. Next is magnetic lines and flux. Flux you all know. Magnetic lines properties also you know. They very importantly remember magnetic lines. They do not originate, they do not terminate. No, absolutely not. That's a vital or a very important difference between electric field and magnetic field. Electric field lines, they start at positive charge and terminate at negative charge. Magnetic field lines don't. And that has a very important implication. In Gauss theorem, the flux of electric field over a closed surface becomes total number of charges enclosed. But in magnetism, it is always zero. I'll come to it in a while. But I do recommend you to do a parallel study of a magnetic dipole, which is the smallest unit in magnetism, and an electric dipole. Do a parallel study about their magnitudes, direction, their fields, how do they originate, how do they terminate, how do they behave, what is the dipole moment, what are their directions. Do a parallel study. That's a very good insight and practice into electrostatics and magnetostatics. Flux is to flow normally. Remember, if an electric field is flowing normally to a given surface, normally का मतलब होता है perpendicular, then amount which is flowing is called as flux. So typically the flux of magnetic field can be obtained over any surface. If this is the magnetic field, then I can have two components. One is perpendicular to the surface and one is parallel to the surface. I can reject the parallel to the surface. As I said, the flux is defined as a normal flow, total normal flow. So I will take the component which is perpendicular to the surface. The direction of surface is given by a vector dA, which is also perpendicular to the surface. Remember, this is by definition. So the flux is nothing but B into dA, and it is integrated over all the surfaces. If you have to find out the component, in this case it will be a dot product because both are, dA is also perpendicular. You have to take a dot product of dA and B. So dA B cos phi or B dot dA, remember. So this becomes the essential definition of flux in physics. Whichever way you go, if you are looking at electric flux, it becomes E dot dA. If you are looking at the flux of, say, gas flow or water flow, then it becomes V dot dA. So everywhere it's the same. If it's a closed surface, then that is the difference. Remember, I told you to do a parallel study. That is the difference. B dot dA, integral of B dot dA for a magnetism is always zero because there are no origin, there was no end to a magnetic field. Every magnetic field that enters in a closed surface has to come out. It will never terminate inside any closed surface. If a magnetic field is entering, it has to come out. If a magnetic field is coming out from a closed surface, it must have entered from somewhere. So for any closed surface, B dot dA is equal to 0. The recall for electricity, any closed surface, E dot dA is sigma q by epsilon naught. Okay, because there can be charges inside where the electric lines of force terminate, they end, they will never come out. So you can calculate. Here there's nothing to calculate. Okay, so yeah, so magnetic lines and flux is important. These are the basic equations that will help you to do a lot of calculations. Motion in a magnetic field, remember, as I told you, if a charge is moving in the magnetic field, only force component, only velocity component that is responsible for the force is the perpendicular. And if you use the right hand rule, then the motion is in circular direction. In this diagram, magnetic field B is perpendicular to the screen. As you can see, it's shown as cross going inside. The charge is moving this way, V. Now you take the right hand fingers, stretch the palm out, put the fingers parallel to V on your screen. little bit above your screen, then turn it towards magnetic field which is pointing inside. Your outstretched thumb will give you the direction of force which is towards the center of the circle. Now go to the other position and you will find that force is still towards the center. Go to the bottom position and you will find the force is still towards the center. So it experiences a centripetal force and therefore the motion is in a circle. The radius of this circle is given by mv by qb. This is a very simple derivation. You know, the centripetal force mv square by r is equal to magnetic force. You can do that. You get a lot of equations here. Then this is a very important principle. Remember cyclotron, betatron, etc., etc. They all work using this equation. So you can find out the velocity, you can find out the kinetic energy, you can write velocity as 2 pi r by t to find out the time period of rotation, and then to find out the frequency. Also remember that if there is, this is only with the perpendicular component. If there is a parallel component, then that will not be responsible for the magnetic force, but that will make the result helical. So the charges are going to move in a helical way. Do remember that. Next idea in this topic, in this top chapter, is magnetic force on a conductor. Whenever you place a whenever you place a current carrying conductor in a magnetic field, it will experience a force. Reason being simple: when there is a current flowing, then there has to be a flow of charges. Since the charges are also flowing in a magnetic field, they have a velocity. Since they have a velocity, they will experience a force. And the force is given by IL cross B. Remember that direction of L is ascertained by direction of I. So in this diagram, the current is flowing this way. So I is in the same direction. Magnetic field here. Curl your right hand fingers from L to B. A magnetic field is here. You will get I dl sine theta. Remember, it means that you are looking at the perpendicular component of the B, which is responsible for this force. At large, you can write ideal cross B or ideal sine theta. Ideal B sine theta. That's your force. This is a force on a small element. You can integrate it to get the force on any other element. So this formula also has a lot of applications. One of the immediate application is the magnetic torque, which is very helpful in our day-to-day life because it defines the electric motor, the first established by Faraday himself. If you have a closed loop kept in a magnetic field along z-axis, and if it's carrying a current in the loop, then by the token of the discussion that we just had, the if you curl your fingers from I to B, right hand fingers, the thumb will point in this direction. While here if you do, current goes here and here. Here if you do, the force will be in this direction, I to B. Therefore, you get two equal and opposite forces, BIL and BIL, this side and this side, acting like a couple on this loop. Therefore, there will be a torque. The torque acting for rotation is equal to IBA sine phi, which is a very straightforward derivation. I'm not getting into it. But do remember that this torque is important. We use all our measuring instruments like galvanometer, millimeter, voltmeter, etc. Use these principles. They keep a spring for a counter torque to make this. All electric generators, etc., motors work on this. Electric fans work on this. Radio speakers, sound speakers, etc., they are going to use this principle. The torque is given by mu cross B, where mu is the dipole moment of this current carrying loop, which is I times A, and potential energy that it will get or store as the torque act is minus mu dot B or mu B cos phi. So that's a very important application of force acting on a current carrying conductor. Next is electric motor. I'll just go through it qualitatively. So the concept that you have learned, same is here. North pole, south pole, two poles of a magnetic field. Put a loop in this. In an electric motor, remember a current flows from the generator or a battery. So this is a DC battery through which you are flowing a current, and as the current flows, the torque is experienced and this loop starts rotating on these two metal and brush arrangements. Remember, this is a DC motor. Is going to be a very important device of the future because most of the technology is moving. In fact, all automobiles are moving toward electric motors where the batteries are going to operate the motors or run the motors, which is basically using this principle. So once the loop rotates, you can use that energy to transfer it to anything else. Remember, in an electric generator, it's the reverse that happens. So in an electric generator, a mechanical force like moving water, etc., of a hydroelectric plant will rotate the rotor, and an electric field is generated on the other end. Last is the Hall effect. Hall effect is simple. If you have a current flowing in one direction, I'll say along x-axis, and therefore the charges are moving, Vd, charges are moving, and then if you place a magnetic field along y-axis, and as we have just discussed, all the charges will experience a force, and as these charges experience a force, they will they are going to drift either upward or downward depending upon their polarity. In this diagram, positive charges will drift downward, negative charges will drift upward, and as a result they will establish a potential difference and an electric field along the z-axis. Okay, so this is typically called as Hall effect. In easy words, I can say if along one axis there is a current, along other axis there is a magnetic field, then along the third axis you will get a potential difference or an electric field actually. So the formula for the Hall effect is here. N is the charge density, do remember, and Q is the charge. So it will help you. I mean, J is current density, By is your magnetic field, Ez is the electric field created or potential difference. Ez can also be written in terms of potential difference. What is important here is what it can be used for. So you can find either N, which is the charge density, or you can find Q, which is the charge or charge polarity, with charge with polarity. Remember, if the polarity changes, the drifting will change its direction. So this can be used Hall effect can be used to figure out these two: the concentration of charges, number of free charges per unit volume, and charge value and quantity. Okay, so we can stop here, I think. Thank you.